Hello and welcome to our screencast about the Variability Extraction and Analysis toolkit, VEXA for short. VEXA was developed by FEDeV to help with different tasks of variability extraction, feature analysis, metrics generation, and visualization. In this video, we will discover some of VEXA's capabilities and how they can be of help in a variability analysis of a real-time operating system, which we'll use as a case study. VEXA is a collection of complementary algorithms with the purpose of facilitating extraction and source code analysis. Toolkit thus covers two of the three pillars of the overall methodology you can see on the slide. For visualization and result exploration, existing frontends can be used. In this screencast, we will utilize the Neo4j browser, a web application with simple graph visualization support. VEDeV, developed by ScopeSat, is a tool that offers more sophisticated visualization capabilities. A separate screencast for VEDeV can be found on the Revamp project website. VEXA builds upon the Neo4j graph database that it uses as its primary storage backend. In summary, VEXA is a plugin for the Neo4j database that runs inside the database itself, thus leveraging the powerful processing capabilities of Neo4j. In addition, a variety of existing Neo4j graph algorithms for search, clustering, ranking, and so on can be easily incorporated into custom source code analysis. The VEXA toolkit follows a methodology flow that starts with model extraction, followed by the VEXA analysis backend. For extraction, VEXA employs so-called adapters, which take as input software engineering assets such as C, C++ code files, Excel files, and many other, and generate graph abstractions inside the graph database. The underlying storage model is a property graph model. Everything is modeled as nodes and relationships with properties. After all abstractions are generated, various analyses can be run. In the live demo section of our screencast, we will write our own custom analysis using the VEXA toolkit. So what are the main features? VEXA is a collection of functions and procedures for variability extraction, feature analysis, code metric generation, exploratory code dependency analysis. VEXA is a plugin for the graph database, where the runtime environment can be a standalone application or a server where the graph database is deployed to. Supported operating systems are Windows and Linux. And VEXA supports tool integration. Because VEXA functionality can be called from all Neo4j drivers, a lot of languages are supported. For example, Java, Go, Python, C++, and so on. There's a support for binary protocol called Bolt and also REST API support. For example, the integration with VEDeV is realized via the Bolt protocol. For our use case, we are going to write a custom analysis and generate custom code metrics using the VEXA toolkit. As our case study, we use the Erica real-time operating system. The operating system is interesting because it implements the AutoSAR standard and is OSA compliant. So let's dive in and start the live demo. For our live demo, we are using the Neo4j desktop application. It's an application for easy setup of new databases. For our use case, we created the Erica 3 database, and we need to check if the VEXA plugin is available. Just click here and open the plugins folder and check if the plugin is there. In our case, it's there, so we can run all the VEXA functionality from within the database. You can also set specific settings in the settings tab. But let's switch back to the desktop and run the Neo4j browser. VEXA and all VEXA functionality is built upon the Cypher query language. Everything you can do in VEXA, you can call from within a Cypher query. The easiest query you can call is the help query. So just call help with a argument VEXA as a the string, and a new window will appear where you can check all the available queries you can call with some text and some signatures. Everything VEXA generates in the database are nodes or relationships. So before we can run our analysis, let's set up some constraints and also some indices. One constraint is that all the projects we create, in our case it's just only one, the name is unique. Also, we set the indices to speed up the analysis process. I cannot explain all the Cypher queries in detail, but you can read them up in this tutorial, which will also be available on the revamped website. So before we can run our analysis, we need to clear the database. As you can see, there were no elements in the database, so nothing was deleted. The first thing you need to do to run an analysis is create a project. In our case, we want to give it a name, Erica3 use case. To do that, we run this query, and a new project will be generated. If we open the database information tab, we can see all node labels, relationship types, and property keys. As we can see here, one node was created. But running an analysis with just one node makes no sense. So we need to add resources. In our case, we add the source code folder of the Erica operating system as a resource to our analysis by running this query. As you can see, another node was created. We can check the simple graph where it gets interesting. So everything is a graph within the graph database. You have nodes, in this case our project node, that has a link to a resource. For our use case, we just need one resource. Currently, VEXA only supports local resources, which are stored on the file system. To analyze these resources, we need to initialize the project. By initializing the project, VEXA will analyze the attached resources and scan them. As you can see, a lot of nodes were created because VEXA realized that the root folder of the source of the operating system contained other source files and directories. So it analyzed the whole file system structure. We can have a quick look how it looks like. So again, we can see in orange the resource node, which is adapted by an adapter, which we call, in this case, the file system adapter, which will generate the directory abstraction. If we open that node, we can see there are a lot of other nodes, and the graph grows bigger and bigger when we run the analysis. But for now, let's leave it at that. So, but just generating the file system structure is not something we want, because we are interested in the compile time variability of source code files, especially in the if-def preprocessor statements inside source files. And to extract that information, we need to run special adapters on source files. But first, we need to match all source files we can find. So let's have a quick look. We get a table as a result. We can see the file name and the extension in the file. We can check if we want to analyze all of them. So yes, we do. So we run the VEXA resource adapt procedure, which which analyzes all those files and extracts this variability information we're interested in. This can take some minutes. In the meantime, we can check out the VEXA data model. So let's call a helper function called epoch meta graph, which will display the data model in graph form. First glance, it looks a little bit messy, but let's clean it up a little bit. So we have again our project node, we have again our resource node, we have our file and directory abstractions. But what we're really interested in is the variability information. And variability information is modeled using these three nodes. The blue node represents a code block. A code block is a piece of code enclosed by an if-def statement. If-def statement is modeled using a variation point. And each variation point can have symbols, which can be configuration constants. So this is the main data model in the background we will use for generating metrics, code metrics. So after VEXA finished the extraction phase, you can see the results here. The VEXA toolkit processed around 500 files and extracted the variability information we are interested in. Everything is stored in the graph database. You can see here there are more than 60,000 nodes now and more than 200,000 relationships. With that data in the database, we can generate code metrics, for example. VEXA has some integrated procedures for that. For example, one of them is based on this paper. We can just run the query and see what the results are. As you can see here, the lines of code, number of variation points, scattering degree, tangling degree, maximum nesting depth, and so on. You can also configure the query itself. So for example, we are not interested in the header guards, so we want to exclude them. But also, we're just interested in the if-def statements and the if not defined statements. By using this query, we will get other results, as you can see, if we compare them. So you can fine-tune your analysis. But just using the predefined analysis is not enough, I guess. So you can write your own. And there lies the power of VEXA, because you can use the procedures there, which are there to create your own analysis. In our case, we are interested in the nesting depth of variation points, so we create our own nesting depth analysis. Let's start and get a quick overview by running this query. What you can see is we have the preprocessor symbols and the usage. So as we can see from the results, this symbol is used in more than 3,000 variation points. So that's actually not normal. There's something going on here and we want to investigate. So let's fine-tune our query. What we see, we also generated the source files or a list of source files this symbol is used in. So we get the count and also all the files where this symbol is used. But still, We're also interested in how deep are the variation points structured and also nested. So we run our final query to get that information. Now we have the symbol, the count, the files, and also the maximum nesting depth. And we're looking for that information. When you check out the queries themselves, you will find that no VEXA functions were used. And that shows the flexibility of the whole VEXA approach. You can use pure Cypher queries on the database data to generate your custom analysis, but you can also utilize the VEXA functions. For example, for this kind of analysis, there are some special functions which will generate the exact results, like calculate scattering metrics, detangling metrics, and so on. So this concludes our screencast, and let's switch back to the slides. Our live demo is over, and we showed how we can use the VEXA toolkit to generate code metrics for the Erica real-time operating system, even create our own analysis. So if you need further information about the concepts, the methodology, and the tool itself, you can contact the FZI, either Anton Paule or Sebastian Reiter. Thank you very much, and bye.